Hi, I'm Ray Lansdowne from Krantz, and today I'd like to introduce you to the SCF high-tech HEPA filter system from Krantz. Along with all of the Krantz equipment, this is made exclusively in Germany, in our factory in Munich, and is one of many high-performance HVAC components that Krantz have been delivering for over 50 years into specialist applications such as nuclear, biocontainment, pharmaceutical and such industries. The equipment today is the SCF high-tech SSS unit, which represents the state-of-the-art of technology for HEPA safe change units. And what I like to do is to introduce you to some of the specific features of the product, and later on we'll take you through a full demonstration of the automated online scanning system which is incorporated in this unit. Along with all Krantz safe change units, it's made exclusively from stainless steel. What I'm going to do is just take the maintenance cover off the unit so that we can look at some of the specific features and components of it. For the sake of the demonstration, I've deliberately left the filter itself out for the time being, but we'll put that back in a short while. So, we can see the filter chamber here with the safe change collar. I'll go into some detail on the specific design of this in a short while, but what we'll do first is look at some of the features inside the unit which make it very much different to other models on the market. So this is the inlet side of the filter, so the airflow is coming through in this direction, and what we can see here is, first of all, a rubber bellows seal which fixes this frame to the inside of the housing and creates a Gastight seal across it. That enables the clamping frame, which is this movable frame here, to be fully isolated into the contaminated airstream. The filter itself sits in this area here. What we also have is a scanning bar across immediately in front of the filter face, and further back we can see an array of aerosol injection tubes which enable the aerosol to be injected directly into this chamber upstream of the filter for efficiency scanning purposes. On the outlet side of the filter we have a screw conveyor and a scanning bar with slots milled into it, which enables an automated scan of the filter. This travels down during the scan test and traverses the whole of the filter face to enable any leaks on the filter to be determined. One of the unique features of the Krantz safe change units is that the clamping frame for the filter is held against the filter and forces the filter against the seal using springs. It is only by applying compressed air that the frame is released with pneumatic pistons at the top and bottom, which you can see just here. Once the filter is slid into the unit, the compressed air is then turned off, and the high force springs will then push the filter frame onto the sealing frame on both sides. So what we also have on the downstream side is a clamping face with a slot that travels all the way around the seal. This is connected to a test point on the front of the housing, which enables us, once a filter is fitted, to be able to pressurize here and prove that the seal is sound and that there is no leakage past the seal. So what I'll do in a second is I will put the filter into the unit so that you can see the clamping and the filter seal in action. Right, so I'm now going to place a filter into the unit. You'll notice that the filter has got a gasket on both sides of the frame. That then slides into the housing, right to the back. We then release the compressed air. The movable frame will then clamp both sides of the filter so that there is a gasket here that's compressed and a gasket here on that testable seal frame on this side. The bellows seal that you saw inside the unit earlier on is meaning that there is now no chance of air bypass around this filter and all of the contaminated airstream runs through the filter itself. So in theory, whilst this has a traditional safe change, bags, rings and maintenance cover, one could run this unit as is with no risk of air bypassing the filter. The other area that I want to focus on is the safe change collar itself. These are common to all safe change type housings. What Krantz have done is develop this specifically to prevent a bag being accidentally pulled off the unit during a maintenance or replacement procedure. Often these grooves are relatively shallow grooves and the rings just sit on them. However, what Krantz have done is created a profile where the groove is undercut and here's a ring that I've cut in half, use a hollow profile rubber ring which enables it to be fitted into the undercut groove such that when a bag is fitted, if you pulled on the bag, it actually gets tighter rather than have any opportunity to jump out of the groove and thus detach from the housing. Okay, so I've now fitted a bag with two rings just to demonstrate how robust this seal is. So with the two rings on, I cannot pull this out of the seal, and in fact the harder I pull it, the tighter the rings become. So this bag cannot detach accidentally during a maintenance procedure. The rings have a tag on them to assist during that safe change procedure, which is really important, particularly when you're releasing the inner stub of the bag through another bag. But what I'll do now is fit the bag into the cover and replace the cover. The other thing that Krantz exclusively use is PE plastic bags rather than PVC. The reason that we do that is to ensure that when the heat sealing of the bag is carried out, that the fumes from the heat sealer are not toxic. And whilst the cover itself does have its own compressible gasket, because of the triple seal feature on this housing, the seal around the maintenance cover is less important. So one of the unique features of Krantz HEPA units is that they're exclusively fitted with Krantz Gastight dampers for isolation. This enables the filter unit to be independently fumigated and can be isolated for filter replacement and maintenance purposes. I want to just focus on the detail of the Gastight damper itself. This particular version is a Krantz GDC damper with a manual actuator. But one of the unique features of these dampers is that when they're in the closed position, you can test them from outside of the airstream to prove that the seal of the damper is not leaking. So we'll look at the specific features of that, and then I'll demonstrate the actual leakage test to prove that this damper is closed. So what we actually have is we have a test port here with a double shielded pneumatic fitting, a small inline ball valve to provide an additional safety feature against the contaminated airstream or the airstream of the filter. On the filter blade itself, this one is obviously in the fully open position currently. We have the EPDM seal, and this has a groove profile such that you end up with two sealing pieces which adhere onto the inside of the damper frame. Adjacent to where the test port is a small hole that goes through into the frame such that when the damper blade is closed, that hole is then between the two seals, which enables us to pressure test that using a pressure test device. So I'll demonstrate that in a second, but if we want to just have a quick look at the detail of these seals, we'll be able to move on to demonstrating the test itself. So what we have here is the double seal arrangement on the damper blade. This effectively is a U-shaped seal, creating a space in between two sealing faces, which when the damper is closed, mate onto the smooth inner surface of the damper itself. We have an external test port here with its inline isolation valve and a double shield pneumatic fitting, and on the inside of the damper is a very small hole which connects to that fitting, and that's positioned in such a way that when the damper blade is in the closed position, it aligns with the center of the two seals. That enables us to pressure test from the outside with the damper in a closed position to prove that there is no leakage across that blade, which we'll demonstrate now. So I'm going to close this damper. That's now in a fully closed position. So the test port is now aligned to the inside of those two seals. This is a double shield valve on the end. So whilst I've opened the isolation valve here, this still cannot leak because the design of the fitting will not allow it. Okay, what we'll do now is we'll close this damper and we'll carry out a leak test just to demonstrate what I've just discussed. So we'll fully close the damper, which is done. The valve here is open. The fitting doesn't leak because it's a double shield type, but the corresponding connector has a pin in the inside of there, which opens as that's connected. So we're now connected via this fitting into that space between the two damper blades, and we can generate a test pressure. In this case, we'll go to above 2,000 pascals, so 2 kilopascals. And if there were leakage, this rotometer, the little needle in here, would be above the bottom, demonstrating that there was a leakage rate. If I pump the pressure up slightly more, you will see that effectively that is constant. It's got a very slow fall, but it's not even measurable on this rotometer. So it's well within the leakage criteria of that damper blade. One of the key features of the Krantz high-tech HEPA housings is the built-in automated efficiency scanning systems. These are validated to EN 1822, which is the UK factory test standard for HEPA filters themselves. So what Krantz have been able to do is incorporate an efficiency scanning system into the housings, which will replicate the factory HEPA test in situ. It's a fully automated system and explains what these two blue cabinets are that you've seen in shop till now. And what I'll do is I'll talk you through both of these pieces of equipment, and then we'll run through a full demonstration. So we have two test trolleys. This is the first one, the MAE, which includes the aerosol generator to deliver the challenge to the filters. And it's a relatively straightforward piece of equipment. We have an air compressor here. We have a particle aerosol generator here, a mixing chamber, and then a fan or gas blower at the back, and then a small controller and some electrics which control the unit. This is the tube that comes from the mixing chamber, which we will connect to the housing when we run the test itself. And this unit is fully controlled by the other unit. So there are some connections across from the smaller unit, and this is effectively the slave unit, with the master being the other. So if we move on to the smaller unit, the MMW unit, what we have in here is a PLC controlled module at the top. We then have a number of more sophisticated components. These are particle diluters, 2 in series, which are 100-to-1 diluters, giving us a 10,000 dilution. We have some valves at the back to direct the flow through these. And then beneath, we have a pair of optical particle counters. These are measuring down to 0.015 micron channel. The reason that they're specifically selected for that is that enables us to measure the MPPS, most penetrating particle size concentrations, which is a requirement for the 1822 efficiency test. So we have 2 particle counters, one of which measures the concentration on the upstream side of the filter, or the dirty air, and one which measures on the downstream side of the filter, or the clean air side of the filter. It then creates a comparison between the two, enabling an efficiency measurement to be established. So what I'm going to do is I'm going to set up the equipment now for a live test demonstration. So we need to connect the test equipment to the housing itself. So there are a number of connections. The first of which is the control connection, because the housing itself has no power, despite having a motor-driven actuator. So all of the power comes from the test equipment itself. So that's connected onto here, and that will control all of the activities that go on within the housing, but most importantly the scanner bar, which will travel down the filter during the test process. What we also have beneath there are the connections for the particle counters, so OPC back and OPC in. So what it does is it creates a closed loop of sampling with one line coming from the particle counter into the housing and one going back. So we will connect those, and there is a pair on the downstream side and a pair on the upstream side of the filter. And I'm going to connect all of those. Now, conveniently, the connections on the test equipment tell us which ones to connect to. So there's a small label, so that because they're all identical, I can ensure I'm connecting the right one to the right one. And these are a double shield pneumatic fitting, so they're only open when the connection is made. And you'll see that there are fairly long hoses on these connections, and that enables, in a large plant room where you have multiple housings, it enables the fairly large test equipment to be located centrally and to be able to test multiple housings. So I've connected all of these. You'll see here that there are inline ball valves as well. I will open all of those so that our connections to the housing are fully established. We've got the control connection. That only leaves us now to connect the aerosol tube from the aerosol generator, which is a cam lock type fitting with a ball valve. So we have a Gastight connection from the equipment via the tube into the housing. Now that we have connected all of the test equipment to the housing, so we've got our control unit, we've got our particle sampling lines, we've got the aerosol rig connected to the unit. Everything else now is a fully automated process controlled by the MMW unit. And what it also features is a barcode or QR code scanning feature, so that the specific housing and the specific filter that's under test can be determined by a built-in code. So what I'm going to do before we start the actual test itself is just initiate the scan of the barcode. So it's prompting me on the software to scan the barcode of the housing, which I'm going to do. So each housing has a unique barcode. So that's now scanned. It's now prompting me to scan the barcode on the filter. So this barcode will be unique to the filter cell that is in this particular housing. So now I'm going to scan the filter itself. So that information has now been captured on the software. So now we've got the details of both the housing and the filter captured in the software. We can just confirm the test is ready to run. It then will prompt us to tell us what airflow is coming through the filter. This you would take from your building management system, or you would have already have an idea of what that value is going to be. I know what volume we're running in here, so I'm going to input that value into the software. It then asks me to confirm that the pressure from the aerosol generator is correct, which I know it is. And it now initiates a fully automated test sequence. So the software here is controlling every part of the test equipment, and it will go through a number of stages of setup during that process, which is reflected on the user interface for the software with various parts of that setup process having countdown timers. So it's building pressure up within the aerosol generator, ensuring that all of the valves are in the correct positions. But I'm not actually doing anything at all other than watching the fully automated sequence. So it's now putting the valves into the particle counters in the correct orientation, switching on the diluting stages within this unit to make sure that those are functioning. And it's now running a pre-run of aerosol and driving the bar, scanner bar, to the top to ensure that the scan will start from the top. And on the software, there is a little red line that indicates the position of the scanner bar within the housing relative to the filter. It always scans from the top down rather than bottom up, so it has to return. In this case, it's already at the top, and it runs for about 60 seconds before it actually starts the scan process. So we're nearly at the point where it will start. Okay, so the particle counters are now running, and we'll start to see data populating the screen on the software, and at the same time we will see the red line indicating the position of the scanning bar start moving down as it traverses slowly across the whole face of that filter. The software is set up in such a way that it will take a sample of particles both on the upstream and downstream side of the filter every 1 second. So a lot of samples being taken. Of course, on the raw air side, the dirty side, these numbers are artificially reduced by a factor of 10,000 because we're running through the 2 dilution units. So it will build that into the calculation when it gets to the end of the test. But as I say, fully automated test. Once the filter and housing information is in the software, everything else is fully automated. So now the scanner bar is approaching the bottom of the filter, and when it does reach the bottom, there's a limit switch built into the unit which will end the test, and the bar will then return back to the top position. When that happens, the system will automatically generate an efficiency record or result, which will become your report to prove that that filter is done. I've not intervened with that whatsoever, fully automated. And if I just scroll down the report, this will show us the efficiencies of the various particle sizes, and most importantly, at the end of the report, it will confirm the overall efficiency value, whether or not it has identified any leaks within the filter at the MPPS range, and whether or not the filter satisfies the requirements of H14. In this case, the filter has passed and fulfills those requirements. So there's no manual intervention, the report is fully automatic, and this will be perfectly satisfactory to submit as a record of a robust test of the filter. So, whilst this is highly sophisticated test equipment, one of the main benefits of a system like this is that the training required to use this to test your filters is relatively minimal. Once you have established how to connect the equipment to your filter housings, everything else is fully automated. It is effectively one click to do the filter test. What that means is that you can very effectively do that work in-house without having to engage specialist contractors, which will certainly save time and cost in the longer term, and enables anybody with the appropriate understanding of the connections to be able to carry out that test on your behalf. So it doesn't require specialist contractors to do the work. There's no intervention into the test once it's been started, so the validity of the test is beyond question.